Hello everyone, and welcome to this new and exciting session in which we are going to demo the YoloX model. That is, we are going to show how this YoloX model could be used in detecting objects from input images. And then from here, we are going to train our YoloX model on a custom object detection dataset. From this training, we're going to obtain a new model now, which unlike this previous model, which detects usual day-to-day objects like cars, trucks, persons, handbags, now this custom trained YoloX model will detect fashion items like jacket, shirt, pants, shoes, and bags. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. We've already prepared the data set and uploaded it to our Google Drive so we could access it very easily from this Colab notebook right here. Now we'll go straight forward to mount this drive, mounting Google Drive, connect to Google Drive. And there we go. We have this drive right here. We have my drive, and then we have the data set which has been stored in the Google Drive account. We are going to start by installing the YoloX from the GitHub repository, and then we'll go straight away to train and evaluate our model. But before this training and evaluation, we'll do a little demo so you see how performant this model is. First things first, we're going to clone this GitHub repository, which is the YoloX repository, which we've seen already. So we're actually going to get a cloned version of this GitHub repository in the Colab notebook. So right here, you see we've the cloning is done. And then if you check right here, you see we have now this new folder which pops up. So we have the YoloX folder, and if you open this, you compare it with the GitHub repository, which is this here. And we could see that this repository right here is identical to this one we've just cloned right here. So you could compare this. See, it's exactly the same thing actually. And again, don't forget to start this amazing repo. We are going to change directory, so we're going to get into this YoloX directory. There we go. Add more code cells. Let's add this code cells before the demo. So we have that, and then we now go ahead and pip install the different requirements we'll need in this training process. So right here, let's run this cell. This installation is now done. We could go straight away into the demo. So let's go ahead and download this model. The models right here, that's the trained models, have already been provided. Now recall that when we have an object detection model like the YoloX and that we pass in our image, this model outputs the bounding boxes which shows exactly where objects are found in the image, and also the kinds of object or the class of the objects we have at a particular position. And so the authors of the GitHub repo have already trained this YoloX model on the Coco dataset, making it easy for us to just basically use this model without having to retrain. And then what they've also done is they've created different flavors of this model. So as you could see here, we have the YoloX S, YoloX M, L, X, and Darknet. And what's interesting is you could see how performant these different models are. This is on 100, so this is core on 100. We see the most performant model right here happens to be the YoloX S, XX, and then we have the number of parameters. That's about 100 million parameters. Recall the parameters, which are basically those knobs we have to turn around during the training process to make the whole model intelligent in a way that when you pass an image, the model is able to generate relevant bounding boxes. So here we have 100 million of such knobs, of such weights, of such filters. And then for this YoloX S, we have just 9 million parameters. So depending on your use case, if you have a constraint of, say, you want to have at least 45 mean average precision. So by the way, this is one of the most popular performance metrics used in object detection, that is to tell how good the model performs. And so if you have this as your limit, as you cannot go below this value, then you want to take a YoloX M model going upward. Now in some scenarios, you may be limited by the number of parameters, and because this number of parameters also affect the speed.
with which inference can be run. Recall that this has to be done on a PC. Now, or let's say it has to be done on a computer. Now, this could be a GPU computer, a computer with a GPU. It could be one with a CPU. It could be, say, on some edge device. So you could have this on some edge device like some Arduino, Jetson Nano, some Raspberry Pi. It could also be on a mobile device. It could be on a web browser. And so you have to take into consideration the speed. Now, the speed here is given on an NVIDIA V100. This is a GPU actually. So here they tell us if you run this, like they've done this benchmarking already for us. So if you run this on this PC, it's going to run in, let's say, 10 milliseconds. Now, based on the particular environment you're working on, you would have to evaluate the time taken for you to pass an input image and get the outputs. And so if you're running this on a CPU, for example, let's say we're not doing this on a GPU anymore, and then we're running this on a CPU, which is actually cheaper. That's if you were to use some cloud service like Amazon, Linode, Google Cloud, Heroku, or Microsoft Azure, then we would say, for example, the speeds obviously is going to take more time to run because with a CPU, or rather with GPUs, they are designed to take up these kinds of computations, unlike the CPUs. So here, let's say we have, say, 60. So we have 60 milliseconds, and then here we have 80 milliseconds. Here we have, say, 100. Here we have, say, 150, and then here we have, say, 70. So we're just trying to follow this pattern, although it's not exactly this. So let's suppose we have something like this, and so now what you'll do is, if you would have, like, say, a limit latency you don't want to go above. So if you are dealing with a system where you need a latency of, say, at least or at most, it must be less than, say, 100 milliseconds, so 1/10 of a second. If you have this kind of constraint, then you would want to pick these models going downward. So now you've constrained yourself, like you want to have 100 and below. So let's say 100 less than or equal. So you have 100 and below, and then also you want 45 or rather mean average precision. So for the sake of the latency, this model already is discarded. So we discard this model for the sake of latency, and then we have this three models left. Now we could also discard this one since it's just at 100. So we're dealing with 60, 80, and 70. Now for the sake of the performance, we'll discard this model, and then we're left with this model and this model. But this model actually outperforms this one, and it also takes less time to run it. So you see clearly that if you have this kind of constraints, then you could easily pick out this model. Now in the case where you're having a constraint of, say, less than, so if we don't have this if we modify this constraint and say we want below, say, 65, then clearly the only model which will verify this is this YoloX model right here. So depending on your constraint, you want to pick a model that suits your particular use case. Now, apart from the standard models, they also provide this light models. You'll notice a great change in the number of parameters and also the mean average precision. You see here the mean average precision values are quite low. That's the models are going to perform poorer, but they are quite fast since they have very few parameters. Like this one doesn't even reach 1 million parameters, whereas here you're dealing with we're dealing with 100 million. So this has 100 times more parameters as compared to this YoloX Nano model. Now these kinds of light models are very great for edge devices, or in fact any scenario where the compute resources are limited. So we'll go ahead and pick one model. Let's go with a YoloX S model, and then here we could copy this link. Let's copy this link and then go ahead and download that. So we'll download our model wget, and we have that link. So we run this and we download this model very easily. Now the model is downloaded. let's go ahead and run this. So here we have Python tools demo. So in this you have this tools here which we've seen already. For inference, we're doing a quick demo. We have the image. We specify the model YoloX S. That's the model we're working with. We also specify the path. Now we've had this weights. So we have this YoloX S weight, which we've downloaded. Here is it right here. So we'll copy this in a weights directory right here. We're gonna add a new folder and we call it weights. So we'll basically call that weights, and then we're gonna copy this into the weights. So that's where we're gonna store our weights. That's fine, we have that in there. And then next we have the image on which we're gonna run the inference on. Right here we have this our new data one image. We're gonna put this in the assets. Okay, there we go. We have that in the assets. That's it here. So we'll specify the image. Now we have the confidence given at 0.3, non-max suppression, threshold 0.65, the size 416. We could modify this to 640 since we're dealing with a standard model. For the tiny models, we use 416, and we also save the results. Now let's take a look at this confidence score right here. But before looking at this, what we're gonna do is simply run this cell. So we'll get the output and we'll better understand why or how this is chosen and how you could modify it to get better results. So let's run this here, and there we go. We have the results saved in this folder. So let's get in here, YoloX S visualizations. Let's take the second one, click on that, and there we go. Here are the results we get. So as you can see, we have traffic light, person, handbag. Now it does this because you have the handle, so it picks this one, and then it also picks just this part. Then we have the car, and persons. And so as you may have noticed, this model isn't focused on particularly detecting the fashion items, like say the shoe, like here. It doesn't particularly detect the shoe, the pant, this coat, and that's it. So it doesn't particularly detect this. It just does this general, or rather detection of common objects. And this is because this model has been trained on the COCO dataset, which contains 80 different classes of common objects like cars, person, traffic lights, and many others. And so the aim of the training process will be to update the model's weights such that they now focus on these fashion items. Now let's get back to the confidence score we had looked at previously. If you notice, all the values you have here for the confidence are above 0.3. That's the above 30%. So all these values will be above 30%. So here you have 33. And now if we modify that confidence score, let's go ahead and modify this confidence score. Let's take a confidence score of 0.5. We have that. Let's run this. We run this here, 0.5. Let's get into this folder. Click that open. There we go. Oops, we have this very bizarre output. Now while we're having this, let's check out a confidence score we had. Yeah, we had 0.0 actually. We didn't put the 0.5. So saying you have a confidence score of 0 means everything you see basically will be an object, and that's why you see everywhere we have objects packed up. So what we'll do is we just simply modify this here. Let's get back here. We have a confidence score of 0.5. We rerun that cell, and once that's done, we check the output. That's fine. Let's check the output. Click that again, and there we go. You now see that we only have objects greater than 0.5. So this detection here, the detection, let's take this off. This detection we had here is gone. So this one is gone. The detection of this car is gone, and there was one other detection right here. I think detection of this person, something like that, is also gone. That's because we've decided to consider only detections whose probability of occurrence is greater than 0.3. And so this is a parameter which you want to tweak depending on your data set. So if you're having a kind of data set where getting or working with a confidence score of 0.3 permits you, say, get a better score, then it's preferable to work with this. So this is the aim of the evaluation process. So you could evaluate with the score, with this confidence threshold. You evaluate with a confidence of 0.5, evaluate with a confidence of 0.25, and so on and so forth. So you do all these evaluations, and the one that gives you the best score is the one which you're going to use, because clearly from here 0.3 is greater than 0.5 for this particular image. We don't know whether working with for other images this is going to perform better, but then during the evaluation process you have to do this automatically on all your data set so that you pick out a confidence score which actually permits you get the best out of your model. So let's take this off here. That's fine. And then we could also look at this non-max suppression here. So this, for the non-max suppression threshold, tells us that if we have this 3 different predictions for this bag, this first one here has a score of 0.9 or confidence of 0.9, this other one confidence 0.8, and this other one confidence 0.85. Clearly we would have to consider this one with the highest threshold, but the algorithm or the model only knows that these 3 are trying to predict the same object if the IOU between this highest threshold bounding box and the others is actually greater than 0.65. So that's how this that's the meaning of this year which was chosen. Let's reduce this year and slide a little, and there we go. So that's how this year, this value 0.65, that's what it actually means. So when you pick this value of 0.65, all you're trying to say is consider the 3 boxes to be trying to detect the same object if and only if the IOU scores is actually greater than 0.65. And so in this case, for example, what we'll have is, if we've selected 0.65, we're going to suppose that the IOU between this year and this one, that is, let's outline that, this bounding box and then this bounding box, say let's say the IOU is 0.7. Now we've seen IOU already in the previous session, so you could check out on that. Basically IOU tells us how close together or how similar the 2 boxes are. So if you have an IOU score of 0.7, then we'll consider that these 2 are trying to predict the same object, and in that case we will now compare their confidence scores and simply eliminate this one. So we'll eliminate this one because we know that this one could represent that object without any issue since he has the highest confidence score. And so that's the aim of the non-max suppression process. So right here now we have just this one box, but then since the IOU threshold is 0.65 and that the IOU between this bounding box and this one is actually less than 0.65, then the model understands that these 2 bounding boxes are for 2 different objects, and in that case this one wouldn't be deleted and this one too wouldn't be deleted. Now if the IOU score was say 0.2 or the threshold was say 0.2, then we would have, since we suppose that this IOU is greater than 0.2, in that case we would then have to delete this right here. But you should note that the aim of building a performant object detection model like the YOLO is to ensure that we don't even need non-max suppression. That is, the model tries to carry out the detection such that you don't have other bounding boxes surrounding this which are trying to detect the same object. And so again you have to turn your non-max suppression threshold to ensure that you get the best out of the model. Let's reduce that, and that's fine. Then another very important point we'll have to take note here is the inference time. Here we're given an inference time of 0.6 seconds. That's like 600 milliseconds, and which is quite different from what we expect from base of this, because here it's true the GPU we're using in the Google Colab notebook isn't exactly a V100, but getting the inference time at 600 milliseconds looks quite high compared to what we'll expect. So let's check that out. Let's check our runtime. You notice that here we're using the CPU, actually we aren't using the GPU, so we could change this to a GPU and then save that. Now we'll have to restart the runtime. We run these cells again. So we run this. We're getting this error actually because we have not copied the assets. So let's do that again. We have here assets. We run that, and here's what we get. We see I have this similar inference time, but now we could specify that the device we want to work on, device is a GPU. So we run that cell, and here's what we get. We now have 50 or say 60 milliseconds inference time. Getting back here, it's like 6 times slower than what was given here, but recall we are not using the same GPUs. So if we get back to this, we could do NVIDIA SMI, and then we could check out on the particular GPU we're using here. So this is a free version of Colab, and so you could feel free to use Colab Pro, Colab Pro Plus, so you could have even better GPUs. So here we have the Tesla K80 with 12 gigabytes of memory. So this is the GPU made available to us by Colab for free, and that gives us this inference time of 60 milliseconds. Now, just for testing purposes, let's test out this best performing model right here. So let's copy this link. We'll test out this one, and we'll also test out this YOLO Nano. So let's copy that link out and then get back to the inference. So we're repeating the same process here for this other model, YoloX model. We're gonna download this. It's gonna take more time since it's a heavier model. Notice how this model is like close to 800 megabytes, while this is just 68 megabytes. So this has to be taken into consideration when picking out a model. Anyways, this model is meant to perform better than this one, as it was given in the benchmarks provided by the authors of the paper YoloX. So that's it. We are going to now, let's add a cell just below this one. So we have this code cell added. Let's push this below. Okay, let's copy this and then paste this here for our demo. So we have here YoloXX. So instead of XX, we have YoloXX. Now we copy this into the weights. So we have YoloXX. That's fine. We specify that we're working with YoloXX. Next thing, we have the data, we have the confidence, we have this, and that's fine. Let's take changes back to 3 and device GPU. So that looks okay. We could now run the cell. There we go. Yes, what we obtained, we had close to 400 milliseconds compared to this one here. So this one gave us 50 milliseconds. 50 milliseconds, while this, it has dropped a little, say 300 milliseconds. So this is like 6 times. It takes 6 times more time to run this models compared to this one. Now let's go ahead and look at the outputs to see whether there's some considerable difference. Anyway, as we said, you don't check this only on a single data. You have to run this kind of evaluation on the full data set. Now, what do we notice? We've noticed already that we have the handbag, which correctly detected. We have this car, traffic light. Now it's not a car, it's a truck. So this model does well at doing this. So it correctly sees that this is actually a truck. It sees a person, just as the previous model. It also sees a cell phone, which the other model didn't see. And this time around, we don't have 2 bags detected. So here we just have 1 handbag detected, which is great because there's actually only 1 handbag. And so with this, you start to get the sense of how this YoloX model outperforms the YoloXS model on just a single data. Now we could try out the YOLO Nano. So let's go ahead and copy this link, copy the link, and then try out the YOLO Nano. We'll repeat the same process. We have wget, and then we run this. So this will take very little time because it's very small models here. We're downloading that. Let's scroll down. What's happening here? Let's scroll down, and then we check out the model size. So here is just 7 megabytes of model size compared to this one. It's like a great difference. And then here we have 68. So you just have to choose the model depending on the platform you're working on. Now again, we are going to repeat the same process. So we have this code cell, paste that. And then here it's a nano, so we just have to specify nano. Don't forget to specify this here. It's very important. You have to specify that you're dealing with the nano version of the YoloX model, and that's fine. So let's run this again and see what we get. We're getting this error because we didn't copy this in our weights. So let's copy that in this weights and then run again. And there we go. The smallest model of the YoloX family gives us an inference of 31 milliseconds. So it takes 31 milliseconds for this model to produce an output. Now let's get to see the output like here. So reduce this and then let's check out on the output. The model here produces a person, misses out on the handbag, misses out on the cell phone, does well on the truck, the persons, but doesn't catch this car here, which other models got. So again, we see that the YoloX, let's take this off. We see that the YoloX X version is greater than the S version, which is again greater than the nano version. But then this YoloX S offers a great balance since the inference time is not too different from the nano as compared to the X, and then its performance too isn't that bad. So that's it for the demo. We are now going to go straight ahead into training on our own custom data set and then evaluating this new models we're going to create. We're going to start by copying this data set into this Colab notebook. So let's have this path right here. You can simply copy the path and then paste it out here. So here's the path to our custom data set, and then this is where we are going to store this data set. So in this YoloX we have data sets folder, and then we're going to store this in there. So let's copy that. You see it's quite easy copying this, as this is already in our Google Drive account. So now we have this here, and then we now go straight away to decompress this data. Again, we're going to copy this path, and then you see we want to decompress this data. We're using the unrar command, and then we have this data here. So let's specify the data we're trying to decompress, and then we're trying to specify the location where we're going to store this. So in this data set we have new folder. We're going to call this fashion. So we're going to store this decompressed data in this fashion folder. So that's fine. Let's run this and see what we get. Okay, that's extracting all this data. That's done. Now we could open this, click open this fashion, click open this. You have the annotations. Takes a while to open. There's so many annotations. We also have the images. So let's scroll down. Oh, we can't. Okay. Anyway, let's have that for now. We have this image sets. Open this up. We have for the train and validation. So let's scroll down, and you notice we have this here. So that's it. So we have our custom data, which has been extracted now in this folder fashion. And then since we're trying to, our data sets put in the Pascal VOC format, in this data set we're gonna have a new folder which we'll call VOC dev kit, and then in the VOC dev kit we have this other new folder. Here we have new folder which we'll call VOC 2007 version. Now you could change all these parts, but we're just using this as it makes it easy to follow up with the existing code base. So that's it. We have this VOC 2007. Now we're going to copy these different folders in here. So here we copy this here. We copy this in here. We copy the images. And that's really all we need. So we need these three folders in here. Just this. We have the annotations, we have the image sets to specify the test and validation data, untrained data, and then we also have the images themselves. So here you have your different images. Now let's reduce this and go straight away into training our model. So here we have extracted this data, and now we're ready to train this data, train our model on this data. We're going to use our train.py file to train the model. we specify this here, the version of our YoloX, and then here we're gonna specify this YoloX version too. So in our weights, we're gonna make sure we have this YoloXS.pth file, which is actually the way PyTorch stores the weights. So here we have this stored in here. We're set to train, and so we could simply run this. So let's run this. We're gonna check out on these parameters later. We get in this, and we've been told there's no such file or directory as this. So here they expect to have two versions, like in here we expected to have two versions. Let's get to the data sets of this Pascal VOC data set. So we expected to have the VOC 2007 version and the VOC 2012 version, but we don't actually need to do that. So we're going to modify this YoloX VOCs.py file to take into consideration only this 2007 version. So that said, we're going to get into experiments, example, there we go, experiments, example, and YoloX VOC. Click on this, and we modify this file simply. So here we're going to modify this file. Let's reduce this. There we go. We're going to scroll down and get to this point where they define this VOC 27 and 2012. So going downward, we have that. We have this just right here, this 46th line, and then we're gonna take off this one. So take this one off, and that should be fine. So we have 2007 train val, and that's it. Now what we could also do is specify, let's say we could say we want 2012 or we want custom. We could change this name to custom, and if you change this name to custom, then you would have to modify this name right here. But anyway, let's leave it as it is, 2007, and then scrolling down here for the test we also have 2007, so that's fine. Now before closing this file, there's some modifications we need to make. Now recall that for the Pascal VOC dataset we have 20 classes, whereas here we are dealing with 11 classes. Initially 10, but we added one class that is a top, so we have this 11. So now that's 11 classes. Let's save this file and then see what we get. So we run the training again, close this up, and then wait for the results. Now we get in this as output where we're told this class right here isn't recognized. So what we're gonna do is we're gonna get back into this folders. We get into this YoloX and data, and then you have the different data sets. Okay, we have the VOC classes. We're going to modify these classes right here, so we make sure that these classes match up with what we expect. Let's get back in here. We had the labels. Okay, copy out those labels, 11 labels actually. So let's go now back into this VOC classes, and then we're gonna change all this. So we take all this off from here, and then we paste out our new classes. Now this are actually tuples, so we have to convert all this into these tuples. And there we go, we have our 11 different classes. We now save this VOC classes, close that up, and then go straight away into training. So let's rerun this cell again. As you can see, now training has started successfully. We are going to train for 300 epochs, or we could always reduce this number. So let's scroll up, and then here you could see where we have max epoch 300. So let's stop the training and modify this. So we could change this to say 200 epochs. Let's get back into this folders. Getting back to this experiments, we had the default, and then we had this YoloXS right here. So it's actually example, so it should be this one. Let's reduce this. We have YoloX VOC and that, and then here we've modified this already. So now what we need to add here is self.max epochs. So we have that to be 20. So instead of 300, now we have 20. We save that and we close this. So now we should expect that next time we should have max epoch of 20. It's actually max epoch, not epochs. So let's move this and save that. So we run this cell again, and we should expect to have that modified. So this shows us how we could update each and every hyperparameter or whatever parameter we have set here. So let's run this. We see that the max epoch has now been modified to 20, and then scrolling down, we should expect to have our training start shortly. Let's reduce this and start training with epoch 1. Now we can see here we have the 20 different epochs, the iterations. That's for each and every epoch we go through 135 iterations. And the reason why we have this is because we have 2,692 items. 2692 divided by 16, we have 168. Now this 168 doesn't match with this value right here, that's 135. That's because we haven't considered the training data only. So here we have 2153. Let's get back here, take this off, 2153 divided by 16, and we have 135 approximately. So that's how this 135 here is gotten. Simply gotten from the fact that we have our full data set, and then we specify the batch size of 16 right here. And so specifying a batch size of 16 means if you have, for example, input data, output labels, and then you have a model, you're going to pass in this data in the model in batches of 16. So unlike what we've seen so far, where we're talking about passing each and every data each time into our model, or what we picked here was 16. So we pass 16 samples at once to speed up the calculations. Now it's advisable to take values less than 32. So we could always take 32, and also these values should be powers of 2. So 2 to the 1, 2 to the 2, or first of all 2 to the 0. 2 to the 0 is 1. 2 to the 2, 2 to the 3, 2 to the 4, and then 2 to the 5. So these are recommended values. 2 to the 5. These are recommended values for our batch size. Now this is for the number of machines we're using to train. This is to specify that we're going to use mixed precision. So we're going to use 16-bit floating point. Then getting back to our training process, you see we have the different iterations that we go through each and every batch up to the last batch. Now we have this. Let's scroll down a little. Let's have this here. Okay, so we have that, and then we could see the memory usage. We can see the time for each iteration. Let's shift to the right. We have the time for each iteration. We have the data time, that's data processing time. We have the loss, that's total loss. We have some specific loss values which we're not going to get into all these details, but you should just note that this total loss is made of the IOU loss, the L1 loss, the confidence loss, and the class loss. Now all these loss values have specific roles. For the class loss is a loss whose aim is to ensure that the weights are modified such that the class predictions are correct, while for the confidence loss, its aim is to ensure that the confidence scores are correct. For the L1 loss, it's kind of like a general purpose loss, IOU loss. Then we have also this learning rate, which we have spoken of in previous sessions here, which is given actually, and this learning rate actually happens to drop as we continue training. So you see that here the learning rate is 1.7 times 10 to the negative 3. Here it drops, and so on and so forth. So generally we want to keep dropping our learning rate slightly as we keep training. And then we have, you would also notice that as we keep training, the loss values kept dropping. So we had 12. We started off with a total loss of 12. At the end of this first epoch, we had a loss of 5.1, and then this dropped to, let's get right to the 20th epoch. We had 20 different epochs, so let's get right to the 20th epoch, and there we would have this here. Let's scroll back up to ensure we get that. Okay, so we had the 20th epoch, and what's our loss? We end up with this total loss of 3.0. But mind you, as this loss values may be very deceitful, like you may feel like, okay, now we've done 20 epochs, why not just train for say 300 epochs or 1000 epochs to make sure we drop this loss as much as possible. And this is where the concept of overfitting comes in. So we had looked at overfitting, but now let's look at it in this other perspective. So let's suppose that we're training our model and the loss is dropping. So we started off at around 12, and then now we about 3. So it's kind of like moving this way. So we're having this loss which keeps dropping, and starts dropping very slowly at some point. Now we feel like, okay, let's increase this, let's go in for many more epochs, and that will just be fine. But as we said, this is not a very great approach, or this way of looking at this may lead us to some trouble, because in case you're training on a particular data set and this loss keeps dropping, whereas the validation loss, which also kept dropping, or the test loss, so this is on data, this is the loss on data the model has already seen. So the model always keep adjusting, and then for the validation, it happens that sometimes you may get to a point where the validation loss instead keeps increasing, or the test set loss. So this is data the model has never ever seen, while this is data the model has been seen, or the model has been trained on actually. So here the model keeps modifying its weights to suit this data it's seen, whereas it starts doing very poorly on data it has never seen. So to avoid this kind of scenarios, you have to keep monitoring the test performance while going through this training process. And that's exactly what we're gonna do, because if you keep on doing this, at the end of the day you feel like, okay, after 20 epochs I'm gonna take the weights after the 20th epochs, because for each epoch we have different weights, because the weights have been modified as we go on from say the first epoch right up to the 20th epoch. So you may be tempted to come and take this weight out the 20th epoch and then go ahead and then deploy a model and work with that. But then be very careful, as instead of taking this model or this weights at this point, it's preferable to take the weights at this point right here, at this point where, or the point before the test set started performing poorly, because at this point at least we're sure that our model does quite well on data it has never seen, whereas at this point it does well on data it has seen, but on data it has never seen it does very very poorly. So you have to make sure you choose the best model or the best version of the model, and not the latest version of the model. Now it may happen that the latest could be the best, so it may happen that you have a validation which goes like this, and that's fine, but you have to choose the best and not the latest, and choosing the best is based on the test set and not the training set. So that said, let's scroll back up slowly, and then you would have this model which has been evaluated already. So that's one great thing about working with this YoloX. You would find that, let's go up, let's go right to the first around here. Okay, so at this point you see each time you have saved weights, the weights have been saved each time you keep on training. Now as you scroll down, you'll see here you have this evaluation which is done on the test set. So you see you have 539 elements, which is logical. This is the number of elements we have on our test set. And then you would see the average position for each and every class. You see it does very poorly on the sunglasses, does very poorly on the top, see it's practically 0, and does quite well on the pants and shirts. Now the reason why this happens is because let's take this instead. The reason why we have this happening is because we have many more hat, jacket, shirt, pants, shorts, skirts, dress, bags, shoes, and shoes examples in our data set, whereas we have very few sunglasses and just a single top which we just added to show you how you could add your own classes. So this means that if you have now a data set of 100,000 more images which you're going to add, and this 100,000 more images have many more tops which you're going to label, then in that case this value will rise up and be similar to what we have here. So this tells us already that it doesn't only depend on the model for it to perform well. Its performance greatly depends on the data itself. So you have to ensure that you get as much relevant data as possible, so that when this model is now exposed to a real world problem, the model is able to provide or show the right objects and their respective classes without any errors. Now that said, we are going to scroll down so you could see the different values. You see here we have mean average precision 50, 90, 50, 0.43, 0.66. As we keep going, this is actually on the test set, not the train set. So this is what is even the most important metric we have to look at. So we keep going. You see here we have let's scroll down. Here we have 0.44, 0.68. It keeps increasing slightly, but this year actually penalizes this score a lot. But anyways, let's keep scrolling down. You see this one now gets to 90, so the pans get to 90% mean average precision. Let's scroll. We had 0.44. Now we see our 0.44. Here we had 0.44, 0.68. Kind of like plateaus at some point. And notice that although this plateaus, although we are not having substantial increase in the mean average precision, if you look at the loss values, they keep dropping. So let's note this. We had the 10th epoch. Let's scroll down here and push this slightly. Let's go back up. You'll see that here you see the loss values keep dropping. So at this point we're around 3.6, we ended at 3.8. Oops. Scroll down. Here see 3.4. See the loss values keep dropping. Scroll down. We have this loss values here. This is the last one. You see it goes right up to 2. You see we have a case where we have 2.9. But anyway, we have we could look at this an average loss of about 3.2. That means it keeps dropping. Whereas we see that at the 10 April we had 0.44 and 0.68, and that's still what we still have here. And it even drops, like here it drops to 0.66. This shows us already that what we had said here kind of like starts to happen. So here we're having a situation where on the train set our loss kept performing well, whereas the mean average position starts dropping. So you see here the mean average position for the test set starts to drop. So you see it starts dropping slightly like this. And so it's clear that we need to take the best model and not the latest model. That's why here you see training of experiment is done and the best average precision is 45. So it happens that at some point we had an average precision of 45%. So that's the model we're going to pick. And what's great about working with this again is you just have to get into this YoloX. You get into the outputs. You have this. You see we have best. You see we have the different checkpoints for each and every epoch. That's basically it. So we just have the latest. We have all the different epochs. We have where do we have? Where's one epoch? Anyway, we have all the different epochs, and then we have the best checkpoint right here. You see, they all have the same weight, 68.54. It's basically the same model, but with different weight values. So we have the best right here. So check this out. You have the best. And save weights to this training of experiment is done the best. Okay, so we have the best right here, and this is practically what we are going to be using instead of using the latest. So with this I could simply copy this and put this in the weights. So let's do just that. Scroll down, or we could copy this programmatically. So we could say we go one step back, and because we actually currently in this YoloX here. So but anyway, let's stay in the YoloX because that's still where we're going to copy. We're still going to copy this still in the same directory. So let's have that. We're still in the YoloX, so we no need to do any change of directory. And then we're going to do a copy. So copy cp copy, and then we take this here, we copy its path, paste, and then we get to the weights. So we come again here and we'll copy this path, paste that, and we simply copy that. So we've copied that. Open this up, you have the best checkpoint, and then here you could rename. So let's rename this and say let's say best checkpoint, and then let's specify YoloX S. So that's it. So we have that, and then you have that there. Also notice that there's a difference the weight size. Like this is 68.54, whereas here is 68.75. That slight difference comes from the fact that here we were having 20 classes as the Pascal VOC classes, whereas here we have just 11 classes. You should also notice that this inference time is given here. So we have the average inference time of 20 milliseconds. This is split between the actual image passing through the model and the non-mask suppression operation, which we've explained already. So this two constitute this total average inference time. Now you'll notice also that we have mean average precision and then given 5095 and mean average precision 50. This was also given in the paper, so you have noticed this. You have 50, 0.5 0.95, and that you also have here, you see you have here that the mean average precision 50 generally is higher than the mean average precision 50 to 95. But to understand why this is higher, you have to understand first of all what this actually means. So let's take a look at that. Let's take this off. Now supposing that our model predicts an output. Now to get the output, let's get back to the demo. Demo right here, YoloX S. So YoloX S, we don't need to download this again. We now also have to change this. So yeah, we get into this here, weights, we copy this. So let's basically copy this and then paste it out here. Oops. Scroll that and then paste it here. Okay, so we paste this file path. That's a new file we're using, and then we have assets and all of that. That's fine. Okay, let's run this and see what we get before explaining the concept of MAP 0.5 and MAP 0.5 to 0.95. We're getting an error here, so we're getting some size mismatch right here. And then if we check on this command, we'll see that we shouldn't be using this standard model which was trained on some standard data set. Instead, we're working with our custom data set. So yeah, we specify we're gonna have a file, and then we get into experiments, we get into default, we're gonna have YoloX S right here. So we're just gonna specify this. Basically that's experiments, default, and YoloX S underscore. That's it. We run that again and we should have something reasonable. So wait for that to run. Okay, the errors we're getting here is this size mismatch. And so we told copying the parameter, we shape this from checkpoint this, the shape in the current model is this. Okay, this tells us that we have our custom data, which is we have 11 classes, and then here we have 80 classes. And so we have to modify this file. So here we'll change this from N to F. So we're taking in a file, and then we modify this file such that we specify the number of classes. So we have this, and under experiments, we get to experiments, we default, scroll down, YoloX S, and then we specify the number of classes here. So we have self that number of classes equal 11. Save that, and that's cool. So we now have that set. Experiments and default. Okay, we run that and close this up. So we should have something reasonable now pop up. We have this known type object has no shape. Let's check on this here to be sure that we have this under the assets. Oh, okay, that was deleted, and so we just put that back. That should be fine now, and we rerun this demo. Let's reduce this, scroll up, and we should get something reasonable. Okay, so that is it. So this time around we have 59 seconds or 59 milliseconds inference speed. Let's run that again. Generally the first time it takes a little bit more time. Okay, 50, let's say 58 or 60 milliseconds. Okay, let's now get straight away and check out the outputs. Reduce this. YoloX, where is it saved? You could always check it out here. So it's saved in YoloX S, and then visualize this outputs. Click on that, and there we go. You see we have traffic light, we have a car, we have a boat, we have a traffic light. So note that this is data this model has never ever seen. Now, since the classes we have in here, that's the car, boat, traffic light, don't match up with the classes we expect, what we'll need to do is get into this YoloX right here, data, data set, From here we have this Coco classes. We'll open this Coco classes up, and then we'll replace all those classes here. Let's take all this off with the classes which we expect from the classes in our custom data set. Now, getting back to understand the concept of having mean average precision of 0.5 and mean average precision of 0.5 to 0.95. Let's suppose that will be the model which permits us detect dustbin cans. So supposing that the actual true level is like this, so this is the true level, but then the model does this. So the model performs this way, it predicts this instead. And so here, when trying to give this prediction some precision score, we may be tempted to say that this isn't a correct prediction since it's quite different from the actual prediction. Now, the way we decide on whether a prediction can be rated as valid or not is by having this thresholds. So the thresholds 0.5 simply means that if we compute the IOU between these two here, that's the actual and the predicted, and if it's greater than 0.5, then we consider that the model did well on this prediction, and so this is fine. But if it's less than 0.5, then the model didn't do well on the prediction. So like here, for example, we may suppose that this IOU is like let's say 0.52. So if this IOU is 0.52, then the evaluation or the evaluator will consider that this is correct, and so this is fine. Now, if we increase this from 0.5 to 0.9, then clearly this isn't a prediction. So this wouldn't be considered to be a correct prediction since the IOU here is less than 0.9. And so that's why whenever we increase this thresholds, the kind of values we get, that's the kind of scores we get, become even worse, since now the model is even way more stricter as to what is a correct prediction or not. Whereas when we have this prediction, or when we have the threshold at 0.5, the model is a little bit more lenient, and so a prediction like this one, which isn't like, let's take this off so you see it clearly. So we suppose that the model has predicted this isn't a very good prediction, but working at 0.5, like working at threshold of 0.5, will allow this to pass. So we'll consider this as a prediction, whereas working at 0.9, we wouldn't allow this to pass. Now, when we say we're taking 0.5 to 0.9, it simply means we are taking threshold values in this range, 0.5 to 0.9. So we'll take 0.5, we'll take 0.6 up to 0.8, and finally 0.9. And then what we'll do is we'll get the mean average precision for each and every threshold, and then we'll find the average of all these. Now it becomes evident why we cannot go up to 1, because going up to 1 simply means we're saying that each and every time the actual and the predicted must be exactly the same. But then this isn't very possible. If you do that, then the mean average precision scores you get will be very low. So we give account for some slight differences with, for example, the 0.9, 0.8, and so on and so forth. So if you have something like this, exactly the same year, but with just a slight difference, maybe you may have something like with the 0.9, the model considers this as fine. Whereas if the threshold was 1, then even this wouldn't be considered as a correct prediction. And that said, we now understand the concepts of the mean average precision at different thresholds. So we've gotten to this point where we've been able to train our model on some custom data set and then show how well this model performs on this custom data set. It's important to note that we're able to train this data set, or train this model rather, on our data set in a very short period of time, thanks to the fact that we applied transfer learning. As we've just seen, transfer learning and machine learning permits us to make use of a model which has already been pre-trained. So supposing we have this, let's draw it here. So supposing we have this model which has already been pre-trained on a similar kind of task. In this case, it's actually the same task but with different classes. So we've pre-trained a model A, so let's call this model A, which has been pre-trained, and then we now create a model B by training based off this model A. And so just as we saw at the beginning, where initially we just initialize the weights. So initially we have weights which are initialized as this different parameters for the filters, and the weights we have, even the fully connected layers, normally are just initialized when training from scratch. But when applying transfer learning, we train based off a model which has already been trained on a huge data set or a large data set. So like this case where we had a model which had been trained on Cocoa data set. Cocoa is tens of thousands of data points, and now we're now making use of that model. So this model now serves as our initialization for this new task. So we have this large task, or this task with a large available data set, and now we just have a smaller data set, and we're able to achieve great results because we trained our model from weights which have been initialized from this previously trained data set, or from this previously trained model A. And that's it for this section. See you in the next section, where we are going to train a lighter model like the YoloX Nano, and we are going to integrate 1DB.